Hi, this lecture is about continuous probability distributions, and particularly the standard normal curve, and hopefully how you might learn to use it and use the Excel tools in relation to it. Before I get into that, however, let me just connect back a bit for us. Take a step back. In chapter 2, I think it is, I introduced to you to the concept of distributions, a data distribution. And there was a frequency distribution, and there was another kind of frequency distribution, which was a cumulative frequency distribution, also known as an ogive. A frequency distribution says how many people scored 22 on this test, and you can find out how many people scored that, and that's the height of a column, for instance, or a line on a graph. A cumulative frequency distribution, the ogive, gives you a line that, this may be reversed for you, which starts low on your left and circles up and then curves over, which gives you the total number of cases that have occurred to that point. It's a cumulative frequency. And it gets up the top, and at the end, ultimately top, it's 100%. And it's all the cases ultimately in the situation. Well, last week, what we talked about was discrete probability distributions. That's a distribution of probabilities for discrete data. Now, discrete data, again, is data in which the cases are completely independent. There's no overlap or even connection to them particularly. Number of children is the obvious one in this one. You have 0 children, you have 1 child, you have 2 children, you have 3 children, maybe you have 12 children. Nobody has 2.3 children. You don't have partial children. Nobody if you own number of cars you have or number of pets you have, nobody has 2.4 pets. Nobody has 3.6 cars. You can say, well, I got a car that doesn't work very well and it's been stripped down, so it's only about 0.6. Either you own the car or you don't own the car. You know, it's like it's there or it's not there. There's no in between piece there. That's discrete data, and you get discrete probabilities associated with discrete data. With continuous data, we're limited only by the sensitivity of our measuring instruments. An couple obvious continuous data pieces are height and weight. I watch my weight fairly carefully, and I'm actually pretty pleased with the fact that I'm currently down almost over 25 pounds from where my highest weight has been. I watch my weight really carefully, and I sort of adjust things as I go in this process. But my scale tells me that I am at 208, 208.5, or 209 pounds. Now there's in between points in that. I could be 208.25 pounds or 208.33 pounds, but the scale doesn't have the sensitivity to tell me that. So it measures, gives me discrete numbers, but the underlying variable is in fact continuous. And it's very, and we're limited by our ability to measure it accurately with sufficient sensitivity. You can measure yourself, and you know, like I think of myself as 5'10". Well, I might be 5'10" and an eighth, or a 5'10" and a 16th, or 5'10" and a quarter. You know, it's like, who knows exactly what that is, and depends on how straight I'm sitting, and it depends on the sensitivity of the measuring instrument. We are limited in much of our data collection by the sensitivity instruments we use, and that becomes an important piece of this process. So we end up working with things that looks like it's discrete data, but it's really the underlying variable is a continuous variable, and we treat it as continuous. This comes to mind, the height one comes to mind because this the last couple of weeks I had both a granddaughter and a grandson come over, and they're cousins to each other. And he walks in and I'm going, my God, he's 6'2". He's the tallest kid in our he's the tallest person in our family at the moment. It's like, wow, he's really tall. And a couple of days later, I ran into my granddaughter, and she walked in, and I kind of went, wow, I think she's probably 5'10". She's the same height as I am, though truthfully, she might be slightly more. I didn't get out a yardstick and measure, do all those sorts of things, but she's about 5'10". And the question that occurred to me was like, which one of them is taller? Red flag, red flag. Bad question. The question itself is not sufficiently precise, because you say which one's taller, you kind of look at him and say, well, obviously he is. He's up here and she's here. It's like, obviously he's the taller one. Except my real question in this process is, compared to their peers, which one is taller? Because guys are typically taller than girls are, females are. Males are typically taller than females are. On average, males are taller than females. My question really is, I thought about this one, is relative to their genders, which one of the two of these two is taller? And that's a complex question, because you got to have information about their individual genders. And this gets at what Z-scores standardization gets at for us, allows us to do. It allows us to compare scores from different distributions. And even though the scores, the raw scores may be, well, clearly this one's higher than this one. It's just to say, yeah, but compared to their distributions, this one may be taller or shorter. It's like, how do you make those comparisons when you're talking about different distributions of data? And to do that, what we do is we do a thing called standardizing. And that's what I mentioned here. That's the kind of key question in this process is, the mathematical question is, how do we compare individual scores from different data distributions? How do you decide those things like that? And let me go to something here and come on. Suppose we have a person named Jim here, and Jim takes 2 tests, and on one test A, he gets a 75, on test B, he gets a 95. On which test did Jim do better? And the answer is, there's insufficient information to answer that question. Because I don't know what better means. Which one had the higher number? Well, that's test B. But maybe test B, he got 95 out of 200 questions, and on test A, he got 75 out of 78 questions. Well, it's better 75 out of 78. His percentage is a whole lot better on test A. But it's like, you have insufficient information here because they come from different data distributions. So how do you compare them in a reasonable sort of way? Well, the key to that process is you got to look at means and standard deviations. And I want to, first of all, let me show you something here about how my whiteboard. On a Z-score, Z-scores equal X, your raw score, minus X bar, the mean, divided by standard deviation. Now, just a note for you, the math of this is not very hard. You're talking about doing a subtraction and a division. I mean, we're talking basic arithmetic here. So you can't get too, you can't from a mathematical perspective be too intimidated by this. It's something you got to do, and then you got to figure out what does it mean. but a z-score themselves is actually fairly easy to do. I mean, it's mathematics if it's not hard. There is, can I type in here? No, I don't know if I can. Yeah, let me type. No, I'm going to go that. Let that go for the time being. The mathematics of it is easy. There is a test called standardize. That it's a formula in Excel, and what it does is it does this mathematics for you. With the examples I'm using, like Jim's scores, I'm going to go back to Jim's scores here in a minute, where you're talking about a mean of 60, a mean of something, and a standard deviation of 10, and so forth. Z-scores are really easy. The place where you end up using standardized for getting figured out what the standardized scores are is if I give, I'm not going to, but if I gave you a problem and said, okay, the raw score in this is 0.03356. The mean is 0.04527. The standard deviation is 0.00357. You take those, I mean, I could do that, and probably you could too, but you put it in the standardized and I'll give you this stuff. And it's like, bang, it's very straightforward. But it's useful when your numbers are not easy, straightforward numbers. That's when you want to use a standardized function or the standardized formula for an Excel. Aside from that, I would say it's probably not worthwhile because you just don't use it. I mean, for most cases, the mathematics of it is just fairly straightforward. But I'll do the mathematics here in front of you on this one. Whereas Jim has test A, he got 75, the mean is 65, standard deviation of 10. It's X, 75, minus X bar, or 65 divided by 10, or plus 1. Oh, thanks, man. On the second test, where he apparently scores higher, you have X 95 minus X bar, so you have 95 minus 100. So you have a minus 5 divided by 5, and this gives me a z-score of minus 1. Well, what that says to me is on test 1, Jim scored 1 standard deviation above the mean. On test B, he scored 1 standard deviation below the mean. So by that thing, he did a lot better on test 1, even though his raw score is higher on test 2. Now let me say something about here. Key concepts. You have raw scores, which are the raw data that comes out of something, and you have a standardized score. A z-score is a standardized score. And what it does is it changes between those things. When I give you problems to do, and I'm going to ask you to find the probability or find a score or some such thing, one of the things you got to do is stop and say, first of all, am I working with a raw score distribution, or am I working with a standard score distribution? If you're working with standard scores, what you're going to see is you're going to see a mean of 0 and a standard deviation of 1. So you get a z-score. You are not going to get a z-score of 17. I mean, it could, I suppose. It's theoretically possible, but the probability of it is very, very low. Most z-scores are going to fall between a -3 and a +3. So the first question is, which one am I working with here? The second thing, raw score, standardized score. That's question 1. Question 2, am I asking you for a score, or am I asking you for a probability of a score? Makes a difference. What's this probability thing, Steve, you're talking about here? I guess, so say more about that. Well, the first piece here is, it doesn't matter what your raw data looks like. your raw data can be skewed like this one is, where it's much more heavily to one end. And when you get skewed data like this, by the way, it means that the mode's the smallest score, the median is bigger than the mode, and the mean is bigger than either one of those two. Doesn't matter, could be look like that, could like anything, doesn't really matter. When you standardize it, what's going to look like is this. And the area under this, under the curve here is equal to 1.0. Now, if you do something and the probability comes up 2.5%, no. Probability comes up 103%. You've done something wrong, because you can't have a probability more than one. And if it's something under this thing has specific probabilities associated with it, for any given z-score, for instance, negative 1.5, there's both what's a point probability and a cumulative probability. Now, this point issue came up in the last chapter when we talked about discrete probability distributions also. A point probability would be that I got exactly the score right here. A cumulative probability is I got this score right here or anything to this side of it. Now, for negative 1.5, the cumulative probability is going to be 4.4 plus 1.7 plus 0.5 plus 0.1%, or come about 6.5% roughly. You add those things up, it's kind of 6.5, 6.6, somewhere in that range, is a cumulative probability of getting this score or something less than it. Now, the probability of getting a positive, and here's the interesting thing is, the probability of getting a positive z-score of positive 1.5 is exactly the point probability of getting a negative. The height of these lines are exactly the same. And that's the height, that's the probability of that specific point happening. However, the probability, a cumulative probability of getting a positive 1.5 z-score is the sum of everything to the left here. The cumulative probability of getting a negative 1.5 is everything from this side to the left. Now, clearly, there's a lot more from here over than there is from here over. So the cumulative probability as z-scores get more positive or larger gets bigger and bigger. But the point probabilities will be exactly the same between them. So back to the two key concepts here. These are going to come back in a number of ways. You have raw scores versus standardized scores. These are raw scores. These are standardized scores. And then you've got the question of, am I talking about point probability, or am I talking about cumulative probability? And it makes a real difference about what you come up with. And the area, the total area under this curve is equal to 1. So, I mean, what's the probability of getting some score? 1. You pull a score out, what's the probability of getting a score? It's 1. You know, what's the probability of getting a specific score? Now that depends on where the mean and standard deviation is. And it's less than 1. It's the probability of it. One of the things that comes up and comes out of this little chart here, which is this little graph, which is really important, is the area in this curve, under this curve between -1 and +1 is 68%. What's the likelihood you're going to get a score between -1, a z-score between -1 and a z-score of +1? 68%, 2/3, guaranteed. What's the probability of getting a score of mean or less? It's 50%. Half of it's here, half of it's here. What's the probability of getting the cumulative probability of getting a z-score of 0.5? Well, since this is the middle, it's 0.5 plus 19%, so it's 69.1%. That tells you the probability of coming up with a different score, a specific of a cumulative, the cumulative probability of coming up a score or some score up to that score. Here are the Excel formulas. I'm gonna go to Excel in a minute here and just sort of show you a bit about how to use them. These look, you start reading them and you're going, geez, Steve, the language is really repetitive here. What are we talking about? Well, again, the first question, I mentioned to you standardized. You probably are not going to use that ever. It's probably simpler with most of the examples I'll give you, because most of the numbers I'm going to do generally is I'm going to round things off for you to make it, to minimize the mathematics of it. But if you're dealing with something that's got means and standard deviations that have 3 or 4 decimal points to the right of the decimal, then you might use standardized, because the mathematics gets just more complex and it's not worth the effort from my side. But mostly you're not going to use standardized here. I'll probably give you a question or so where I ask you to do that, but mostly not. Then the question is, do I have a raw score or do I have a standardized score? Norm.in and norm.dist work with raw score distributions. Now I go back here. These are raw scores. So if I've given you said, I'm gonna give you a problem when I ask here in a minute is, what's the probability on test B of scoring less than Jim did? The cumulative probability on test B of less than Jim scored 95. And that's one question. Second question is, what's the probability on test B of scoring exactly 90? Now, how would we figure that stuff out? And let me show you how I'd use Excel for doing that sort of problem. First of all, I'd come down here and say, okay, which one of these tests do I use? Well, we're using raw data, so I'm either using norm.in, INV, or norm.dist, because they're both raw score distributions. And the first one, I'm saying, what I want to know is, what's the probability of scoring less than 95? Well, that's a probability associated with a score. So I'd be using norm.dist for that. And the second question was, what's the probability of scoring exactly 90? Again, I'm looking for a probability associated with the score. So let me show you how I do that using Excel. That's it. First of all, where do you get these things? Pull down. I said what I want to use is I want to use norm.dist. What's the probability? Let me start with the second one first. The probability of scoring exactly 90. So the X would be 90. The mean is 100. Standard deviation is 10. That's correct. Let me go back and double check that. No, it means 100. Test B, if mean is 100, standard deviation is 5. So I was putting in the wrong numbers. Good thing I went back and checked. What's the score of getting exactly 90? Well, when I use the word exactly, we're talking point probability. That probability to get that exact point. Whoops, I don't want that one. So I want false. What that tells me is the probability of getting exactly 90 is about 1%. Not very likely. So here's a question for you. It's like, what's the likelihood I'll score less than Jim? Well, Jim, I could put 95 in here, but that would tell me, and then use a true, because true is our cumulative thing. If I put in true here, it'll give me a number, but that would also tell me is that I get the same as Jim. So let me do 94, which means that I get any number up to and including 94. So look at the probability that I'd score less than Jim on it. The score of 94 or less with a mean of 100, standard deviation to 5, cumulative means but the probability of that is about 11.5%. That's how I end up using these things in this process. It takes some time to walk through it. And again, let me just be really clear here that a first key is when you're working with this area, we're talking about raw scores and standardized scores. And it's really important to understand what you're working with, which one you're working with. Because you go with the functions on would go it's a little bit differently. And the second thing is when I ask you that, do I want a probability or do I want score? And there's two different functions for those things. And the third piece about it is, do I want a point probability, the probability of a specific point, or do I want a point or do I want a cumulative probability of everything up to? That last piece, that language becomes really important. And there's hints in the language. If the question says, what's the probability of getting exactly da 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 da? You're talking point probability. What is the likelihood that Jim, that when you take test A, you will get exactly the same score Jim did? That's a point probability question. If you get a question that says as much as, or up to, or less than, or those sorts of things, then you're using cumulative probability. So those are three key concepts to keep in mind here. Raw score versus standard score. What you're asking for. Am I asking for a point, or am I asking for a score, and I'm asking for a probability? And third thing is it cumulative probability or is it point probability? Those are the three key things to be as you're working through this section to keep in mind. Now, let me just, I'm going to mention, I gave you a Z-score table earlier, and I don't have, I'm not sure I have that available handy here. Maybe. Yes, here it is. I don't particularly want to encourage you to use this but I want you to, if you look at a normal stat book, you're going to find these. You're going to get look at the index of any normal stat book. In the back of it, you're going to find a Z-score table. And what this is, for instance, is, if you have a Z-score of 0, what this tells you is 50% of the population is to the left of that point. If you have a Z-score of 0.01, then 0.503, about 0.504, 50 at 0.5% of the distributions to the left. So you read down these things first, and then if you have more digits, you can read over to get the normal piece of it. They have these for negative, and these are typically cumulative scores. I don't use, I mean, I say once I got a chance to use the Excel formulas, I never use these things, and I don't particularly want to encourage you to use them because it has to be very precise, and you got to make sure you've got the right tables and all that. Whereas the Excel stuff, you'll always have it available. But I just want to mention that I'm not sure I should include it, but I don't want what I do. The reason I include it at all in the class is I don't want you to have, at some point, to have somebody pull out this table and say, well, according to this is these scores. So you say, what is that? I have never seen that. It's like, this is make sure you've at least seen it, but I don't think it's the most productive way of doing it. Now, let me go back here. One of the kinds of questions that comes up, and it comes up in a number of different ways here, is what's the probability that someone will score between 95 and 105 on this test? That's actually a fairly straightforward one. And what that means is, and let me just try and do this. Oh, wasn't what I wanted to do. What's the probability that someone would score between 95 and 105? Now, since I know the standard deviation is 5, that's a +1 and a -1 standard deviation. What I've told you already is that's 68%. That's that middle ground between -1 and +1, 68%. Let me show you how that would look if I were doing that with Excel. But I'm doing this here not with z-scores, but with raw scores. What I would start off with is to say, okay, between 95 and 105. So I figured out first of all, what's the probability, cumulative probability of getting a score up to 105, and that is 84.1%. Now let me go back and say, okay, let me put in 95 now. And the probability of that is 0.158. If I this is equal to this minus this. Lo and behold, it comes up 68%. But that's the process. I mean, I told you that was going to be beforehand, but I use simple things here. I use a simply +1 standard deviation and -1 standard deviation. Suppose I did, let me go back and do that over again. Suppose I want to say, what's the probability to be between, because I don't know this, score of 110. No, let me do it, maybe more messy. But score of 112, mean of 100, standard deviation of 5, true. 99% of the score is going to be less than that. Okay, I'm going to go back and do it all over again. Or this time say a 93. Now, I'm picking these numbers out at random here because I don't have, but that's what it could end up looking like to some extent in a more realistic world. And the probability, the cumulative probability of up to and including the 93 is 0.8%. I'll take this and just bring it across. What I just did there is by grabbing the lower right-hand corner and pulling across, I just copied everything above it. So what I'm saying is the probability of getting the larger number was 99.1%. Probability of getting the lower number is 0.08. So the probability of getting a score between those two numbers is about 91%, 91.1%. That's how a lot of apparently sophisticated problems are done using z-scores. And again, depends. I will change the problems I give you will switch back and forth between raw scores and standardized scores. They will skip back and forth between point probabilities and cumulative probabilities, and they will skip back and forth between asking for numbers or scores versus asking for probabilities. But those are the three key concepts that I want you to come out with this process. So that's sort of an explanation about how to use the Excel functions and how some of that stuff makes sense to me, at least. Good luck with this.